Okay, so there are a large variety of questions which students can be asked at GCSE relating to percentages. They range from the very simple to the very complex, and let me give you a flavour of what some of those questions may be. Firstly, they could be asked just to write a decimal or a fraction as a percentage. So, for example, express a quarter as a percentage or express 0.832 as a percentage. Very straightforward, and I'm not going to go through how to do that. They could also ask you to find percentages of amounts. So, for example, find 20% of 60. Once again, very straightforward, and I'm not going to be covering how that's done in this presentation. I'm certain that you know exactly how that's done. Okay, also calculating percentage change. Now, people do forget how that's done, and there's a simple formula which will help you calculate percentage change, and that formula simply is change divided by original times 100. An example of a question like that is something like, my house increases in value from £110,000 to £120,000, find the percentage change. Naturally, the calculation you're going to do there is 10,000 divided by the original, which was 110,000, times 100. They could also be asked to express one amount as a percentage of another. For example, express 17 as a percentage of 25. Now, that can confuse people a lot, actually, until you realise that they're just saying, write 17/25 as a percentage. That's relatively easy to do. That could even come up on a non-calculator paper, because 17/25 is the same as 34/50, which is the same as 68/100, and so it's 68%, because, as we all know, percent is simply French for per hundred. That's exactly what percent means, per cent, per hundred. Okay, now we're going to get into some of the things which I'm going to be looking at in this presentation. They're also often asked to find the original amount after a given percentage change. Now, this is normally described as a reverse percentage. Now, students find it very difficult to even identify when a problem is a reverse percentage problem. The key thing to recognise is they're asking for the original value after they've given you the change after a percentage increase or decrease has been affected. So, for example, a pair of Wellingtons are reduced in a sale by 30% and now cost £49. How much were they originally? Now, we'll talk about the common mistakes there in a second, but the answer is, of course, £70. Percentage increase and decrease they could be asked to do. They could be asked to decrease £58.70 by 37%. That's considerably easier if you understand percentage multipliers, and we're going to be talking about that in this presentation. And then lastly, they can be asked to perform calculations which find simple interest and compound interest. Now, I hope you recognise there is a distinction to be made between simple interest and compound interest. Most of the time, students will identify with simple interest as the way they would do it if they were calculating percentages, because simple interest is where you don't take into account how much is in the account, say after 1 year, and then perform an interest calculation on that sum after 1 year, and then on that sum after 2 years, and so on and so forth. Compound interest, obviously, is where the amount your account grows by grows each year because you have more money in the account at the end of the year. And that compound interest, I always argue, is far more common in the real world. It's certainly the way bank accounts work. That said, GCSE questions have been asked about simple interest before. Common mistakes. Well, let's take a look first at identifying the percentage multiplier when decreasing by a given percentage. We're also going to take a look at reverse percentages, and we're certainly going to take a look at applying compound interest or depreciation quickly and efficiently. But let's take a look first at identifying the percentage multiplier when decreasing by a given percentage. Okay, percentage multipliers. Most students are happy to accept that if we want to increase an amount by 4%, we need to multiply by 1.04. This makes a lot of sense. The 1 keeps the value there. If you multiply anything by 1, it maintains its current value. And 0.04 is, of course, 4%. That's what 4% is. Just like 0.5 is 50%, 0.04 is 4%. So multiplying by 1.04 keeps the original value there, then adds on 4%. And so it gives you the answer straight away. If the question is increase £70 by 4%, just do 70 times 1.04 and you've got the answer. Likewise, if you want to increase an amount by 17%, the easiest way to do it is to multiply by 1.17. The difficulty comes when students are asked to find the multipliers for reductions or decreases. For example, if I want to reduce an amount by 13%, what would I multiply by to get that answer instantly? Well, the answer is, of course, 0.87. Now that's because if you're reducing something by 13%, you're really finding 87% because you're knocking 13% off, leaving 87% of the original value. So the easiest thing to do is simply to multiply by 0.87. But students find it quite hard to grasp those reduction or decrease multipliers. Now, they'll always say, can I not just do it my way? Can I not just multiply by 0.13 and then subtract that from the original answer? Now, my answer to that is yes, but you're going to really struggle if you're trying to do compound depreciation problems because you cannot do it the long way then. In fact, if it's 7 or 8 years compound depreciation, they're going to really struggle with that. So it's well worth insisting on them learning the percentage reduction multipliers, or you'll come unstuck a little later on in the syllabus. Reverse percentages are also a problem. In fact, I would say it's one of the things which really confuses students. The first thing they have trouble with is just recognising that the problem is a reverse percentage question. A good example of this would be the following question. A radio sells for £63 after a 40% increase in the cost of price. Find the cost price. Now, I'm just going to ask you to pause the video for a second and ask yourself, what do you think the common mistake will be here? What do you think the student will do? Okay, I hope you've had a second to think about that. What most students do when they get this wrong, in fact I would say this is 99% of the time the mistake they make, is to find 40% of 63 and knock it off. And you can understand and sympathise, I'm sure, with why the student would expect that to give them the correct answer. Now the reason it's incorrect is that 40% increase in the cost price was in the cost price, not on the new value of the radio. The radio sells for £63 after a 40% increase on the original value, not 40% decrease of the final value. That does not represent the same amount or the same calculation. Now, if they've got to find the cost price, there's two different ways of thinking about this which I teach. Firstly, we've got, and I argue this way is the way if you're in a non-calculator paper, and they can be given this on a non-calculator paper. Well, we know after a 40% increase that we've actually got 140%. So 140% is £63. Now let's find 10% by dividing both sides by 14. That gives us 10% is £4.50. Now we can just simply multiply by 10 and we get 100% is £45, and that's the original cost of the price. Now that's one way of looking at it. The other way of looking at it is a kind of percentage multiplier setting up an equation method. I simply argue that the original cost was multiplied by 1.40 and our answer was 63. So if we want to work out the original, we need to do 63 divided by 1.4, and that will produce the original cost, which was £45. Okay, I hope that helped, and I hope you can see that there will be times when you're teaching reverse percentages where students get very confused. Okay, for compound interest and depreciation, this is confusing because a lot of them haven't got the hang of the multipliers, but also they forget the kind of formula that you need for compound interest and depreciation. Let's take an example question. In a recession, a house loses value at a rate of 6% per year. If it was originally worth $240,000, how much would it be worth 4 years later? Now, the common mistake seems to be assuming that this is simple interest, not compound interest. What a student does is multiply the 6% by 4, coming up with a figure of 24%, and then starts to reduce 240,000 by 24%. But that is not compound depreciation, because it's losing 6% year on year. So when it loses 6% of 240,000, it loses more value in that first year than in the next year, because the next year it's worth less. and that's why compound depreciation and compound interest are quite confusing. Now, all we need to do, and I'm sure you recognise this calculation, is 240,000 times by 0.94, that's the relevant percentage multiplier for a 6% decrease, and then I'm going to put that to the power of 4 because I'm doing this 4 consecutive years. That gets me the answer straight away and is far more effective at getting the answer immediately, and that's what students need to recognise. I know I've often said in the past, and I still stick by this, that it's good if the students use different methods. I would argue though that this is one of those situations where almost any other method will be inefficient and will lead to incorrect answers in a lot of different cases. If they were, for example, to do 240,000 times by 0.94, write that answer down, then times that by 0.94, write that answer down. It takes a very long time, and those are seconds and minutes which could be spent far more valuably elsewhere on the GCSE paper. Okay, that concludes percentages. Let's have a look at direct and inverse proportion. Now, I'm going to give a couple of problems to you here. I really like direct and inverse proportion. It's good fun to teach. Let's consider the following two problems. Firstly, 24 ounces of sugar are needed to bake 3 cakes. How many ounces of sugar are needed for 2 cakes? And secondly, if it takes 3 men 4 days to build a wall, how long will it take 2 men? Now, my question to you is this: what are the similarities and the differences between these two questions? Pause the video and have a little think about what that might be. Okay, let's have a look at the answers to those problems and also the answer to the question of how they're related. Now, the first question, we were considering a situation with cake and the sugar required to make a cake. Now, it should be intuitively obvious that doubling the number of cakes requires doubling the number of ingredients. Now, whenever you've got a situation between two variables where doubling one involves doubling the other, or trebling one involves trebling the other, or, whatever scale factor you like, when they're related like that, we describe that as directly proportional. So the cakes are directly proportional to the sugar in that first situation. It's relatively easy to solve now because we need to make 2/3 of the number of cakes, and that means we need to use 2/3 of the amounts of sugar, so the answer is going to be 16 ounces. For our second problem though, it is different, because doubling the number of men building the wall should surely halve the time it takes. It's not going to take twice as long with twice as many people, or at least that is certainly not what is implied by the question. So workers and time are inversely proportional to one another. We describe it as inversely proportional where doubling something involves halving another, or trebling something involves thirding another. That is inverse proportion whenever two variables are related like that. So to answer the question, as it takes 3 men 4 days to build a wall, it should take 1 man 12 days to build the wall. 1/3 of the workers 3 times longer. And therefore 2 men should take 6 days. Double the number of workers should be half as much time. Now, those are two lovely wordy examples of direct and inverse proportion. Next slide please, Paul. Let's have a look at now what I like to call my students the funny fish symbol, just because I think it looks a little bit like a fish and it helps them remember that there is this new symbol which they occasionally include in the GCSE. So it's very much worth them recognising this symbol. Now, I'm going to show you a systematic approach for solving the two problems we just did. Let's let S stand for the ounces of sugar and C stand for the number of cakes, and treat that funny fish symbol as standing for is proportional to, because that's what it means. So we immediately recognise that cakes and sugar are directly proportional. That allows me to write C funny fish sign S, or C is proportional to S. Now, this is an important idea what comes next. We are always allowed to trade the proportional sign for an equal sign, provided we include a constant of proportionality which is multiplied on one of the sides of the equation. That is just a straight up fact which they need to understand. There's a good reason for that as well. If any two quantities are related by doubling one involves doubling the other, or trebling one involves trebling the other, then they are directly proportional, but it also means that their general equation would be y equals kx, where y and x are the variables. Essentially it would be represented by a straight line equation on a Cartesian axis. Any straight line equation involves direct proportion between two variables, provided the straight line equation goes through the origin. And therefore we can trade it and make it c equals ks. Just make sure your students are aware that the proportional sign can be swapped for an equals as long as you include a constant of proportionality. We can now find the value of that constant of proportionality by using the two known values of c and s. Now we knew that 3 cakes took 24 ounces of sugar, so I can write 3 equals k times 24. I can then easily establish the value of k, 1/8, and now I can use that back in the equation, c equals 1/8 s, or c equals s over 8, and now I can just plug in c as 2 and work out s, and I can see s is 16 ounces. Now what I like about this approach is that it works also when you're dealing with inverse proportion, and it certainly works in exam contexts as well. Okay, let's have a look at the funny fish symbol in inverse proportion. If we're looking at the last problem, letting m equal the number of men involved and d equal the number of days involved, I've just realised that it's horrendously sexist to have men building a wall, so if you want to talk about women, that's absolutely fine. Sorry about that. Okay, if two quantities are inversely proportional, then one is the reciprocal of the other in terms of the proportional symbol. Essentially this is a multiplicative inverse. It's often called the reciprocal function as well, and what it means is, you know, I said doubling is halving, timesing by 3 is thirding. Well, that is 3 1/3 or 4 1/4. That is the reciprocal function in maths, and so we have this expression, m is proportional to 1/d. After we use that, we apply the swap of the funny fish symbol for an equals sign, and we include a constant of proportionality which we must multiply by, and 1/d times k is simply k over d. So I now have m equals k over d. I now proceed as before, and I use my initial conditions of the number of men was 3, the number of days it took was 4, and I can easily establish the value of the constant of proportionality. K will be 12. I now have an equation connecting m and d, so I can write that m equals 12 divided by d, and now I can plug in my new value of m, which was 2, and obtain the value of d as 6. And that's simply all there is to it. Now, the reason why I use this approach is because that is how we would normally expect to do exam questions. Let's have a look at this typical exam question. We have the shutter speed s of a camera, which varies inversely as the square of the aperture setting f. When f equals 8, s equals 125. Now this was a genuine exam question where they didn't use the words proportional to. They preferred to express it as varies inversely. Now this is why the students need a rich mathematical vocabulary, and in fact even outside of the mathematical terms in this question, the fact that they've used the word aperture, which is particular to the field of photography, is going to put a lot of students off. So, you know, there's plenty of reason why they need actually a really good grasp of the English language when completing this paper. But anyway, we've got to find a formula for s in terms of f, and then hence or otherwise we've got to calculate the value of s when f equals 4. Now if you're feeling confident, please feel free to pause the video and have a go at that. If not, I will now run through how it's done. Okay, so we write s is proportional to 1 over f squared, because s was indeed inversely proportional to the square of f, because it said well, s varies inversely to the square of the aperture setting. That gives us s equals k over f squared, because I'm allowed to swap the proportional symbol with equals and apply a constant of proportionality. I now plug in what I'm calling the initial conditions. They're essentially the one condition you were given the question, and that was that s equals 125 when k equals 8. I can then obtain the value of k, because 64 times 125 is 8,000. Thus I can now have the equation which they asked me to obtain, which is that s equals 8,000 over f squared. And now I can answer part B, because in part B they asked me to find the value of s when f equals 4. Simply plug it in and you've got s equals 500. I hope that makes sense. I hope that this was useful and just reminded you of a few ideas which do crop up in the GCSE and you might not have seen for some time. Okay, I hope you enjoyed the presentation. Bye bye.